Hello everyone, I hope you are all doing good. In this session, I'm going to discuss about the module 3. It consists of two methods. First one is momentary method and second one is conjugate beam method. The main aim of these two methods is to find the slopes and deflections at different sections in the beams and frames. Let us see the point by point. The momentary method is one of the most effective method for obtaining the deflections in beams and frames. Right? In this method, the areas of bending moment diagrams are used to determine the slopes and deflections. So that's what is given in this statement. So the area of the bending moment diagram is utilized for computing the slope or deflections at particular points along the axis of the beams. The third point is there are two momentary theorems. The first theorem which gives the slope and the second theorem which gives the deflections. You can see that one theorem is used to calculate the change in the slope between the points on elastic curve, and the second one is used to compute the vertical distance between a point on the elastic curve. Suppose I have a beam something like this, right? The beam is deformed something like this. This is the deformed shape of the structure. Suppose if I want to find the slope at here, so I can have to use the first theorem, momentary first theorem. Suppose if I want to find the deformation from here to here, then I have to use the second momentary theorem. So let us see the derivation of the momentary theorem, and after that we'll look into the few problems. So the derivation of the momentary method. Figure A. This is the figure A. Here you can see that I have taken the simply supported beam which is subjected to the uniformly distributed load, and that this is the deformed shape of the beam, and I have taken 2 points here, point A and point B, right? So here in the point A, I have written the tangent to the curve, elastic curve. In the point B also, we have written tangent to the elastic curve, right? Here the angle between the tangent with respect to horizontal is theta A, the angle between the tangent with respect to horizontal is theta B. So the angle between these 2 points is called as a theta AB. That's called as a change in slope between the 2 points. This is called as a theta AB. The change in slope between the 2 points. That's what the momentary theorem 1. Let us see the statements here. Figure A shows the elastic curve of a loaded UDL simple beam. On the elastic curve, tangents are drawn on points A and B. The total angle between the 2 tangents is denoted as theta AB. That's what I said, that the total angle between the 2 tangents is called as a theta AB. In order to find out that theta AB, consider the incremental change in the angle d theta over an infinitesimal segment dx. So here on the elastic curve, what I have done is, so I have taken a small elemental strip. So from the elemental strips, I have drawn the lines somewhere it is intersected. That's the point O, since it's a curvature, and the angle is d theta, radius r, and the length of this strip is dx, and that is located at a distance of x bar from the point B. There you can see that located at a distance x bar from point B. Now for this beam, the bending moment diagram is written BMD, right? This is how the BMD is. So whatever the strip is taken, I have written here the strip dx, and this is the center of gravity, and MA by EI and MB by EA is moment at this section divided by whatever the EI value, flexural rigidity, right? So BMD, this is also called as a M by EI diagram. So in the module 3, we use this wording everywhere, M by EI diagram. It means the bending moment value M divided by EI value corresponding EI. So that's called as a M by EI diagram. The radius of curvature and bending moment for any section of the beam is given by the usual bending equation. We all know that bending equation M by I is equal to F by Y is equal to E by R. So I have taken this relationship M by I is equal to E by R, that is considered as a equation 1, where R is the radius of curvation, E is the Young's modulus, I is the moment of inertia, M is the bending moment. Now the elementary length dx and the change in angle d theta are related as. So here I have taken the elementary length here. So we know that the length of the arc is s is equal to r theta. So in the place of s, dx is there. So dx is equal to r into d theta. So that's what it's written here. Dx is equal to r into d theta. So again, dx by d theta is equal to r. So that is called as equation 2. Substitute equation 2 in equation 1. So whatever the equation 2 is there, you substitute in the equation 1 in place of r. So now again, that can be written as d theta is equal to m by I e into overall into dx. So that is d theta is equal to m by I into dx. That's called as equation 3. The total change angle theta AB can be obtained by integrating equation 3 between points A and B, which is expressed as. Suppose here you can see that d theta is the angle between these 2 points, right? This is the d theta, right? Suppose if I want to find the total change in angle between point A and point B, I have to integrate this portion. So that's why I use here theta AB is equal to integration of A to B d theta, right? So integration of A to B, d theta is equal to whatever this value is substituted here, m by A into dx. Again, theta AB can be written as theta B minus theta A. It means change in slope between 2 points. That's equal to integration A to B, m by A into dx. So this is called as a first moment area theorem. So you can say the first moment area theorem, integration A to B, m by A dx. In general, we can write slope theta is equal to integration m by A into dx. That's also written can be written as area of BMD divided by EI. So EI is as usual. So integration of m is area of BMD. So the statement of the first theorem, the change in slope between 2 points on a straight member under flexure is equal to the area of m by A diagram between the 2 points. That's what I said here in the change in slope between these 2 points, that's equal to area of m by A diagram between these 2 points. Suppose if I have written the Benjamin diagram, right, from here to here, so the change in slope between A to B, that's equal to area of Benjamin diagram between A to B. That's the first theorem. We'll move on to the continuation of the derivation. The distance dy along the vertical line through a point B is nearly equal to, it said nearly equal to. So if you come to this diagram, here you can see that this is the dy, right? Whatever the strip is taken here, right? So you draw one line from here, again the tangent to here. So this is the dy. So that's what the vertical line is written from point B. This is the point B, and which that will wait. We'll go to the equation. So dy is equal to x bar into d theta. So we have a triangle here. Here you can see that. So d theta is equal to, so this is a x bar. X bar is a distance between the strip and a point B and dy. So using these parameters, we can arrive with this equation. Dy is equal to x bar into d theta. Integrating the y between points A and B yield the vertical distance yba between the points B and the tangent from A on the elastic curve. So if you integrate this, dy value between A and B, the tangent is written from a point A and which cuts the vertical line. That will give the deflection. So that's what it's written. Integration of y between points A and B yield the vertical distance yba between the point B and the tangent from a point A on the elastic curve. So this tangent is written from point A. So that's called as yba is equal to integration of x bar d theta. So integration of yba is equal to integration of dy, that's equal to x bar d theta. Integration of A to B, we know that already the d theta value from the equation 3, d theta is equal to m by A into dx. So that is substituted here. So m by EI into x bar d theta, so dx. YBA is equal to, so integration of A to B, m by EI into dx x bar. So this is called as a second moment area theorem. So YBA is equal to area of bending moment diagram into x bar divided by A. Right? This is the equation we are going to use to solve the problems. So YBA is equal to area of BMD into X bar. The term is added here, X bar, right? In the first theorem, we have theta is equal to area of BMD divided by A. In the second theorem, YBA is equal to, the deflection is equal to area of BMD into X bar divided by A. So that's it, the derivation. So we'll look into the statements of both theorem 1 and theorem 2. Theorem 1, the change in slope between 2 points on a straight member under the flexure is equal to the area of M by A diagram between those 2 points. That's what we have seen. Theta AB is equal to theta B minus theta A is equal to integration of A to B M by A dx. In general, slope is equal to theta is equal to integration of M by A dx is equal to area of BMD divided by A. So this is the equation we are going to use this to solve the problems. Theorem 2, it says that deflection at a point in a beam direction perpendicular to its original straight line portion. Suppose this is my beam, this is a deflected shape. If I am want to find the deflection somewhere at here, right? This is a line which is perpendicular to the original portion. It's written here, original straight portion line measured from the tangent to the elastic curve. Measured from the tangent to the elastic curve at another point is given by the moment of M by A diagram. It means tangent to the elastic curve is somewhere here, somewhere we can take any point. So tangent to elastic curve, right? Now moment of this area, moment of this M by A diagram taken about this line. So that's called as a theorem 2. The deflection at a point in a beam in the direction perpendicular to its original straight line portion is measured from the tangent to the elastic curve at another point. Tangent to elastic curve is another point is given by the moment of M by A diagram about the point where deflection is required. So tangent to the elastic curve another point, moment of M by A diagram. This is a, suppose if you write the M by A diagram, that's bending moment diagram divided by A value. So that moment of M by A diagram should be taken about the section where deflection is needed, where deflection is required. Deflection y is equal to same integration of M by A into X bar into dx, that is equal to area of BMD into X bar divided by AI. So few areas and centroid which are necessary to now to solve the problems. So we'll see the different shapes first. So first one is the rectangular shape I have taken. So rectangular shape, we all know that the area is equal to B, the length, that is h. So breadth into height. Centroid is equal to, suppose centroid is over here, this side also B by 2, this side also B by 2. Triangle, this is a triangle, area is equal to half into base into height. So from here to here is 1/3 of base, and from here to here is 2/3 of base. Right portion, left part. Parabola, generally we see the parabola something like this, right? So they have taken half of that portion here, right? So here you can see that the parabola, the centroid is this one. The area of this parabola is 2/3 into base into height. And centroid is always at a distance of 3/8 times of B from the straight edge, and remaining this side to this left part is 5/8 times of B. The total length is B. So you can see that area is equal to B by, so area is equal to 2/3 into B into H. X bar is equal to in this side 5/8 times of B, and right part is 3/8 times of B. So this we have to remember because it's very, very necessary when the beam is subjected to uniform distributed load. The next is parabolic spandrel. The parabolic spandrel is, you can see that it varies like curved in nature. It's not the straight line here, right? This is a B, H. H means any bending moment value depending on loading case. The area is 1/3 into base into height. And right part, the centroid locates from the right edges at a distance of 3/4 times of base, that is this one. And left part, the centroid is at a distance of 1/4 times of B. So let us see the procedure for finding the slope and deflection using the momentary method. First, calculate the reactions if it is necessary. draw the BMD, boundary conditions we have to check, calculate the slope, that is slope theta is equal to area of BMD divided by EI. This is very important. That's the only formula we are going to use. Calculate the deflection. The deflection Y is equal to area BMD into X bar divided by EI. Let us see the problems on the cantilever beams. The problem number 1 is determine the slope and deflection at free end using the momentary method. So the problem is given here, a cantilever beam which is subjected to point load at a free end. So now we wanted to find the slope and deflection at free end. Let us rewrite the diagram. So this is again same the given problem. So always we know that whenever the cantilever is subjected to loading, this is how it bends. I'm writing the curve here, right? This is a arcing shape. That's why it's a negative bending moment. And again, the maximum deflection happens at the free end, that is YB. And also draw a tangent to this deflection curve, that's theta B. The maximum slope also occurs at the free end. We are aware of this diagram, this sign convention, right? So this is a section, left clockwise, right anti-clockwise positive, and reverse is other part. Suppose this is suppose it is anti-clockwise here, and again it's clockwise, right of the section is negative. The bending moment sign, I think this is studied in the strength of materials. So now, whatever the beam, the cantilever beam is given, first draw the BMD. We know that P is acting, P into L is PL, that is bending moment about A. The bending moment at A is equal to minus P into L, because it is, if I take a section here, this is acting clockwise, right of the section, it's a negative. Okay, so this is again with a point load. Whenever the point load is acting, the bending moment always varies linearly. Now you can see that boundary conditions. Boundary condition at point A. Point A is a fixed support. We all know that fixed support, the slope and deformation is, vertical deformation is 0. So point B, theta B is theta max, YB is Y max. That's what we have to find it. Theta B, theta YB. Calculate the slope at free end, right? To calculate the slope at free end, that is here, I said that momentary theorem 1, we have to use it for the slope. What it says is the change in slope between 2 points. Suppose now I can see that this is the 1 point and this is 1 point, right? Suppose my elastic curve is something like this, right? So the slope at this point, we all know that 0, right? So I have to take the slope between 2 points. Among those, 1 point is, we have to find it, other point is where the slope is 0, right? So that it is easy to find the slope at free end. So 2 points we have taken, theta B minus theta A. Change in slope between the 2 points, that's the statement of the momentary theorem 1. Change in slope between 2 points, theta B minus theta A, is equal to area of BMD between those 2 points, B and A, divided by A. So already we know that boundary condition, theta A is equal to 0. So theta B, area of BMD between B and A. So how to calculate area of, this is a BMD diagram, area of BMD between B and A. So this is a triangle, apply the half into base is L, height is equal to minus PL. So negative bending moment. So half into L into minus PL, that is minus PL square by 2EI. That's the slope. It's just a one-step calculation. Next, calculation of deflection at free end. So again, Y max, we know that the maximum deflection occurs at the free end. That's the equation is area of BMD between those 2 points, B and A, into X bar divided by EI. So EI is constant in the problem, right? So again, area of BMD is equal to half into L into minus PL. So X bar is, here you see that. So once we have written the bending diagram, we have to take the centroid of that centroid, and also X bar, we have to take it from the centroid to the point where we wanted to find the deflection, right? So many students may be having doubt, centroid to this side. No, we should not take to this side, because the reason is we are not calculating the deflection here. So wherever we are calculating the deflection, to that point we have to take the X bar value. So it's X bar is equal to 2 by 3 of L. So X 2 by 3 of L, substitute, and finally it will be YB is equal to minus PL cube by 3A. So that's it, that problem. Similarly, one more problem is given here. Calculate the slope and deflection at free end using moment area method. Now you can see that the same cantilever beam is subject to uniform distributed load. Draw the deflection curve. We know that YB and theta B will be maximum at B, right? So whenever the uniform distributed load is acting, so here it will be the shape of the bending diagram is always parabolic. If the point load is acting, the bending diagram is linear variation. If the uniform distributed load is acting, the bending diagram is parabolic in nature. That too here it's a parabolic spandrel, right? So what is the bending moment value? Here WL square by 2, because W into L is the length, WL into L by 2. That's the WL square by 2 is the bending moment at A. The calculation is given here. So boundary conditions, again, if you want, you can write it, otherwise you can leave. It's not necessary to write each and every time boundary conditions. If it is known to you, then you can leave that step. Calculate the slope at free end. The same again, theta B minus theta A. So B and A, we want to find the slope at here with reference to A. So already theta A is equal to 0. Area of BMD between B and A same, divided by A. A is constant. So here you can see that we know that area of this parabolic spandrel is 1 by 3 into base into height. So 1 by 3 into base is how much? L. Height is WL square by 2. That is minus WL square by 2. So you can see that 1 by 3 into L into minus WL square by 2 divided by EI. So that's the slope at B. Calculate the deflection at free end. Again same, YB is equal to area of BMD into X bar divided by EI. So area, we got it from this figure, bending diagram into X bar. Now you can see that X bar from the here, the centroid to point where we have to find the deflection. Right, X bar is equal to 3 by 4 times of L. Those diagrams are already given in the above slides. So you can see that area of the BMD and 3 by 4 times of L. So that's this deflection. Again, we'll move on to next problem. Calculate the slope and deflection at free end using the moment area method. Now you can see that uniform distributed load up to a length of L by 2. This side is there is no load acting on the cantilever beam. So redraw the given loading and draw the bending diagram. We all know that whenever the uniform distributed load is acting on the cantilever beam, it's a parabolic spandrel, right? So again, the intensity is WL square by 8, because W into L by 2, it is a WL by 2 into L by 4, it becomes a WL square by 8. The calculation is given here. And again, it's a negative. We all know that if you take the section here, the load will be acting something clockwise right of the section, it's a negative. So boundary conditions, fixed support 0, and free end we have to find it. So change in slope as per the moment area theorem 1, theta B minus theta A. Theta A already we know that 0. Area BMD between point B and A divided by A. Now area BMD between point and B and A, 1 by 3, this is spandrel, into, here we do not have any bending diagram, right? So whatever the length is there, that one we have to consider. 1 by 3 into L by 2 is the length of the diagram, and intensity is minus WL square by 8. So that's the slope at B. Again, deflection at B. So again, same equation, YB is equal to area of BMD into X bar divided by EI. So this is the area of BMD, this one, into, so there you can see that X bar here. So now we wanted to find the deflection at here. So take the centroid, from the centroid to end of this diagram is 3 by 4 times of the span, whatever this length, that's length is L by 2 plus L by 2. Now you can see that, so 1 by, this is the area of that BMD into X bar is L by 2 plus L by 2. This one is L by 2 plus whatever this distance. So 3 by 4 times of L by 2. So you calculate, that will be the final value of this deflection at free end. Then the next problem is calculate the slope and deflection at free end using moment area method. Now you can see that a cantilever beam is subject to a couple M at free end. Draw the bending moment diagram for that, right? The bending moment will be rectangular whenever the couple is acting at free end. It's a rectangular, negative. The bending moment at A is minus M, because take the section like this. So it's acting clockwise right of the section, it's negative. Boundary conditions, theta B minus theta A. So I want to find the slope at B, theta B minus theta A. Theta A is the change in slopes, theta B minus theta A. Theta A is already 0. Area of BMD between B and A divided by EI. So area of BMD between B and A is L into minus M. L into minus m divided by a. So this is the slope at B. So deflection at B, YB is equal to area of BMD between B and A into x bar divided by A. So whatever the area of the BMD, first we calculate the area, then again you take the centroid moment of the this BMD area of BMD about the section where we wanted to find the deflection, that's called as x bar. Here x bar is L by 2. So the finally the deflection, vertical deflection at free end is minus ml square by 2EI. So thank you very much. We will discuss the remaining problems in the next video.